Inscribed angles. An inscribed angle is an angle with its vertex on the circle and sides on chords. An inscribed angle should not be mistaken for a central angle. A central angle has its vertex at the center of the circle. The inscribed angle is going to have an angle on the edge of it, which we'll see a picture of in just a moment here. Inscribed angles are going to have a very particular property, which is difficult to describe deductively. So what we're going to do is look at a couple of examples of inscribed angles and inductively create an idea that would be our property. Okay, and since I'm going to be doing this inductively, what I'm going to do is draw two different circles. Let's check spacing here first. Okay, so about here should be good, I think, for our first. All right, that was pretty good. All right, and then for a second one, I'll just go ahead and set it up. What did I use as my measurements? Out there. I think that'd be the same one. All right, so I got a couple of circles here. An inscribed angle is going to have its vertex on the edge of the circle. Okay, so let me identify a couple of points here. Let's go ahead and call that A. Let's call that B. Then as a third point, I'm going to use point P because in the previous video, I had used C as the central angle. Okay, so I'm going to choose a point out here. Let's call that P. And if I connect like that, that creates a chord, which is referred to over here. Connect right here for another chord. This is what we call an inscribed angle. Okay, instead of having the vertex over here, at that location, at the center, the vertex is all the way across on the other side of the figure. All right, the property that we're going to be looking at is directly related to the central angle that shares the same intercepted arc as our inscribed angle. That would mean this central angle. Let's go ahead and call that C. All right. The property that we're going to look at, which is really about the size of the inscribed angle, is going to be directly related to the size of the central angle because they have the same intercepted arc. All right, and with an inductive approach, what I'm going to do is just measure the angles, which I might need to extend out my lines a little bit. Okay, let's see, let's extend out this one. I can take that out afterwards. Okay, so if I got that center pretty good, we're getting about 100 and maybe 12 or 13 degrees. Let's go with 112. All right, the inscribed angle, let's take that out there. I suppose I'll need to extend this out a little bit too. Okay, the inscribed angle, which will be an acute angle here, right? It's smaller size. That, let's see if I can get this to center correctly. That looks like it's just past 55 degrees. So let's go ahead and call it 56 degrees. You get 56 degrees. All right, now, I believe, yeah, the numbers came out really good here. Okay, what we want to do is make an observation about the size of these two different angle measurements here. And the comparison here is that the inscribed angle is half of the measure of the central angle with that same intercepted arc. Okay, if I took 56, multiplied it by 2, I get 112. All right, the fact that I was using a protractor and I got numbers that worked out perfect here was really cool. Sometimes they end up just being a little bit off because of how we measure things, but this actually showed the property perfectly. Okay, the inscribed angle is going to be half the measure of the central angle that shares the same intercepted arc. All right, since that example worked out really good, for the second picture, what I'm going to do is show you a special case. Okay, let's not use a minor arc to start things off. Let's use a semicircle. Let's do that. Let's actually draw a diameter. Okay. All right, and for letters, I'm going to go ahead and use the same thing here. Let's just call that A. Let's call that B. let's go ahead and call that C, right there. Okay, so the angle that's right here, which is 180 degrees, right? It's 180 degrees, is going to best represent ACB here. It's just been opened up to 180 degrees. Let's go ahead and add in an inscribed angle, which means that I need point P. Okay, let's go ahead and put point P just over here. Okay, I'm going to make it a little bit more interesting and not put it directly at the top there. All right, so I'm going to connect to A, connect to B. That's going to be point P. I'm going to change the color of these to match the other ones, just because I want. Cool. All right, the central angle, of course, that is 180 degrees. It's a semicircle. Okay, now if things hold true for what was shown here, that the inscribed angle is half the central angle with the same intercepted arc, which we're using here, AB, half of 180 would be 90 degrees. That should turn out to be exactly 90 degrees. And it didn't matter where I actually put point P. It should just turn out to be 180 degrees. All right, to verify that, what I'm going to do is take a sticky note. Okay, instead of using a protractor, I'm going to take a sticky note and just go ahead and show you that it fits perfectly. Well, it should. So like unstick itself for a moment there. It's going to fit perfectly right there. All right, that will be 90 degrees. All right, and then what's really interesting about this is that you could put point P anywhere. You could do P way over here. You can put it in that spot. And if I connect P to A and P to B, and because that inscribed angle still uses A and B as the intercepted arc, which is valued at 180 degrees, the measure right here should be 90 degrees. And there you have it. P could literally be anywhere along that curve and you would get a 90-degree angle. Let's go ahead and summarize our findings. An inscribed angle cannot have the same measure as the intercepted arc. Okay, whatever the arc measure is, it can't be the same thing as the intercepted arc because it does not have the same measure as the central angle, which matches up to the intercepted arc. However, there is a relationship. The relationship that we found was this. The measure of an inscribed angle is half the measure of the intercepted arc. Okay, we really looked at it as being half of the measure of the central angle, but the intercepted arc has the same measure, so we could also write this, that the inscribed angle is half of the measure of the intercepted arc. And where that helps out is when you have pictures that show the inscribed angle, but not the central angle. You'd be able to relate the inscribed angle to the intercepted arc that it creates. For example 1, we're going to find the measure of the red arc or red angle that we have here. In the first picture, we've got a red angle. That's going to be angle G that we're looking to figure out its size. Okay, and it intercepts, this is an inscribed angle here, it intercepts the arc HF, which is going to be valued at 90 degrees. Okay, now what we don't see in the picture here is a central angle. But if we were to draw one, I could connect from D to F, which, if I can get that lined up correctly there, which you can see appears to be a 90-degree angle. Okay, so remember that the central angle measure is going to be the intercepted arc's measure. That's going to be the arc measure here. The inscribed angle, which extends all the way to the other side, but intercepts that same arc, is going to have half of that measure. So that means that the measure of angle G is going to be 45 degrees. For the second figure, we're going to be looking in the opposite direction. What we want to do is figure out the measure of this arc here, the measure of arc TV. Because the inscribed angle over at U, which intercepts that arc TV, is 38 degrees, you can actually double it to get the measure of the arc. Okay, it's 2 times 38, and that turns out to be 76 degrees. That'll be 76 degrees there. For the third figure, we're going to figure out the measure of angle X. Okay, so here's the red angle that we've got. We're asked to figure out that measure right there. Okay, the measure of angle X is equal to something. Okay, and of all of these, this might be the most interesting one here, because the information that we have is located in some other angle over here, which is that 72 degrees over in y. Okay, but the interesting thing about it is that y, if you follow out the sides, it intercepts the arc from z to w. It intercepts that, which means that the arc measure from z to w, not the question that we're being asked here, but the measure of that arc is going to be double the 72, which is going to be 144. Okay, but angle x intercepts the exact same arc. It's going to intercept zw, so you would divide that by 2 to get the size of x. So if all we're going to do is multiply the 72 by 2 to get the arc zw, then divide it by 2, we come to the same value. The measure of angle x is equal to 72 degrees. Next, we have something pretty interesting to look at here. A polygon is an inscribed polygon if all of its vertices lie on the circle. That would mean that all the points of that polygon are going to be on the edge of the circle. The circle containing the vertices is a circumscribed circle. Okay, so we got inscribed, which means to be inside of something. Circumscribed means to be around something. Okay, and we are going to complete this statement here. The opposite angles of an inscribed quadrilateral. Let's make a point here that we are talking about a quadrilateral in this case, not some other type of a polygon, no pentagons, no hexagons, no triangles. This is something that is strictly just going to be for quadrilaterals. We're going to complete this statement that the opposite angles of an inscribed quadrilateral are blank. All right, to begin this, it's going to be easier to start with a circle. I don't think that I actually have to have the center for this, but I'll go ahead and just plot it just to show it. Let's make sure I get everything to fit on the screen here too. Okay, so that should work. Okay, so I'm going to start with a circle because it's going to be easier to make that quadrilateral inscribed into the circle versus attempting to draw a quadrilateral and hoping that the circle is going to pass through all of the points. Sometimes you can't even do it. Other times when you can do it, it would be really difficult to figure out where the center is. So it's easier to construct it with the circle first. All right, so as a quadrilateral, I need 4 points. My attempt here is not to space them equally. I don't want to make a square. Let's go ahead and just put a point right there. All right, so I'm going to connect all of these, and that will be an inscribed quadrilateral. All right, and what I want to do is discover something about the opposite angles. For this picture, I'm going to choose not to label any of the vertices because it might get a little bit confusing with the other things that I'm going to show. But what I am going to do is point to 2 angles and say these will be my focused angles, which will be here and here. So I'm going to look at those as the opposite angles. The argument for the other 2 will be exactly the same thing. My attention is just going to go to these 2. All right, so what I'm going to do is I'm going to describe the measure of this angle as x degrees. It could be anything, I'm just going to call it x degrees. But if that is x degrees, and I follow out these sides here to an intercepted arc from here to here, the measure of that intercepted arc is going to be twice that measure, which is 2x. Okay, I'm going to go ahead and take out the degree symbol so I don't have to use that for the rest of this. Okay, so if this is x degrees though, this is going to be 2x degrees. It's going to be twice as much. If that's 2x degrees, the other side of this might not look too pretty here, having a circle around another one, but let's do this. We'll put little arrows on them so it looks like they stop at some point. If this is 2x, then this major arc needs to be the difference from 360. So I could describe that major arc as 360 degrees minus 2x. Okay, and then if I follow it all the way to its edges, here and here, this intercepted arc, I can call that an intercepted arc to that segment and that segment, is going to be twice the size of this inscribed angle. So if I divide that by 2, I get 180 minus x. Okay, and despite the fact that it might be confusing with all the extra curves that are around it, if we now look at the 2 opposite angles that we have here, we can build a relationship between them. If we add those two together, if we take x plus 180 minus x, if I take those and add them together, the only reason I put parentheses here is just so you can see the two separate angles. But if I add them together and I drop those parentheses, the x's will actually cancel out, and we get 180, which tells us that the opposite angles of an inscribed quadrilateral are supplementary. For example 2, we're going to apply our newest property, which says that if we have a quadrilateral inscribed into a circle, the opposite angles are going to be supplements. Okay, so for the first picture, what we want to do is match up the 80 degrees with the x. Those are going to be supplements to each other, which means that x is equal to 100 degrees. We would also match up the 75 with the y, so y is going to be equal to 105 degrees. And that's it. For the second picture, these two are going to get matched up here. Those two need to be supplements to each other, so what we'll do is go ahead and add them together. That gives us a total of 6b, which would have to be equal to 180. We divide by 6. B is going to be equal to 30. All right, and then for the other two that we have there, they're both going to be the same measure because they're both 2a. But what we're going to do is we're going to add them together. We're going to say that 4a is equal to 180. Divide that by 4, and you get 45. And that's it.
Wait, there was.